Imagine pumping dark liquid through a bottom pipe so it goes surging up into three completely different glass vessels. Our brains naturally assume that a massive, heavy volume of water sitting in a wide, bulbous vase is going to push down with more force than the tiny sliver of water inside a narrow tube. But as the liquid settles, the water stops moving entirely. The fluid levels out to perfectly match across all three drastically different shapes. This diagram shows a physical phenomenon known as the hydrostatic paradox. You can clearly see the uniform water level matching perfectly, indicated by the identical height markers labeled H. To figure out why this balanced system seems to defy basic logic, we have to stop looking at the shape of the containers entirely and instead investigate the invisible forces holding the fluid in place. Let's isolate a theoretical column of water suspended in a larger tank. We label its top and bottom area A and its total height H. Water above it pushes down, creating our first downward force. The water inside the column also has its own mass. Gravity pulls it down, adding weight as a second downward force. To keep it from sinking, surrounding water below pushes back up, holding it in place. Any volume of fluid sitting at rest is trapped in this strict mathematical equilibrium. The downward weight is perfectly supported by the upward pressure. This handwritten derivation translates those exact physical forces into math, starting with the equilibrium equation. Force 1 plus weight equals force 2. We expand the weight variable into its physical components: the cylinder's area, its height, fluid density, and gravity. Look what happens next. Because the area variable is present in every single term, it mathematically cancels out. If we measure from the absolute surface, the initial top pressure pushing down is simply atmospheric pressure from the sky above. The math proves it. The width, the total volume, and the specific shape of any fluid column have zero effect on the pressure at its base. These two images side by side show our original oddly shaped vessels next to our newly derived pressure formula. Let's run the final variables. All three containers share the same room, so the atmospheric pressure pushing down on the open tops is identical. They contain the exact same blue liquid and exist under the exact same gravity. Density and gravity are perfectly constant. This boxed equation provides the final proof. Since area is mathematically irrelevant, the pressure at the bottom depends exclusively on the height of the fluid. In the real world, this means a 1-inch wide pipe stretching 100 feet straight down into the earth exerts the exact same crushing pressure on a sensor as the bottom of a 100-foot deep lake. Fluid pressure is dictated entirely by depth and density. This allows engineers to calculate the crushing weight of the deep ocean without ever needing to account for how wide the ocean itself actually is.